Good afternoon, everyone, and welcome to the Cosmic Mining webinar. Just explain how we're going to do this. I'll do a quick introduction, and then I'm going to update you regards the project resources. There's a very little things to note to make it a bit more successful for the students. If you have got students present, I appreciate if you could just drop into the Q&A box that you've got some students present, and if you could tell us how many, that would be even better, because it gives us an idea for when we're reporting to the trustees how successful and how positive our webinars are. Then I'll hand over to Dr. Olivia Jones. She's not going to do a form, it's going to be a presentation by her, and she's going to talk us through the actual update of James Webb and some key pointers about identifying spectra. And then there'll be a chance for questions at the end. Again, if you use the actual Q&A box, and Neil will be monitoring that online as well. So without any further ado, activity 4. And if at any point you're not getting audio and visual, can you just let us know via the chat box, or just send me an email and I'll pick up on that. So you will possibly recognize this from previous years for the staff, but certainly for the students, once you've completed your activity 2 and you've done your 10 no targets, and I've had a look at them and I've sent them back to you, then you're given about 50 targets to identify. And this is the spreadsheet that you require to fill in, and the AOR keys are there. So you go to cases, open it up, and then complete these boxes. And that's what the training presentations are about, for you to understand how. But a couple of things, please do take care and read the information. One of the key things I'm finding when people are returning is the fact this box here, it says spectrum cuts off after 50 microns, yes or no. If you click yes, that automatically will grey out these two boxes, because it's not relevant, because if it cuts off after 15, you can't identify a broad feature at 18, and certainly not at 25. So what I'm finding is people are still putting data in there, and the way I'm marking these, comparing to another spreadsheet, it's starting to get a little bit confusing. And to be honest, if you're reading this, you shouldn't need to fill those in. Same for high-res spectrum available, yes or no. To find the high-res spectrum, see this one available, you literally just have to scroll all the way down, and if it's there, it will be there. All right, and if you click there, that will give you further information, such like if there's a redshift. So those are the two key things I want people to just pay attention to. And teachers, could you please complete this? Because if I just get one sent back through the upload facility, and it just comes to me as phase 2 activity, phase 2 underscore CM underscore activity for 2024, I have no idea what school, where it's coming from. So if you could complete that data. And attention to detail is really important, because when you start looking at the unknown ones, when we're sending them forward up to STFC, they're not going to have a clue where they're coming from. And also, it's about skills. And if you're going to be data, you have to be precise, you have to be complete. You can't just submit partially filled forms. But anyway, I'm going to pass over now to Dr. Jones, because I'm conscious time's moving on. Final thing, phase 4, that's the artifact. I know it seems a long way away, but we are already planning for conferences. When it comes into the new year and there's a chance to come to conference, please do take it. Don't worry if you've not completed the 50 known ones or anything like that. You can actually do your poster about the skills you've learned, what you've done so far. And also, you could actually maybe pick up an individual item and then go and do a further analysis of it. All right, so that's just a little bit of an idea to start thinking towards. after Christmas. Now I'll hand over to Dr. Jones. So over to you, Libby.
Hello, everyone.
There we go. Yeah.
Can we go to my slides, please?
Yeah. There we go.
Okay. So it's a pleasure to talk to you all. I'm an astronomer based up in Edinburgh, but I've also worked at Hubble and Webb mission control. And I work on space telescopes and the data analysis from that and taking spectra and also some pretty pictures. And so we're trying to expand from Spitzer data, which you're looking at as part of the Cosmic Mining Project, to find interesting objects to look at with JWST and go back again. So can we go to the next slide, please? So the Spitzer Space Telescope used to work from 3 to 160 nanometers in space. And that overlaps partly with the James Webb telescope, which is new and shiny, which launched on Christmas Day in 2021, and will be the great observatory operating for most of the next 20 years or so. And that slightly hits the optical, but on the very red side of the optical wavelengths, and then overlaps with Spitzer in the infrared. And it's the infrared part that is the most exciting for discovery space. So can we go to the next slide, please? And the telescope, JWST, is very pretty. This was it in the laboratories, the clean rooms in California before it was launched. And you can see this massive mirror, which is about 6.5 meters across, made up of 18 segments. It's super lightweight. And then this sun shield made of a material called Kevlar, which I think is just a cool name, at the bottom, which had to fold out. And so this launched on Christmas Day. And then for the next 2 weeks, all this was all folded up and then it expanded out. And since then, it's at least it says a 10-year mission was the goal. We are looking on for 25-year mission. And the good news is this: unlike Spitzer, which ran out of coolant, which let you take spectra, Webb can take spectra but not run out of any materials, so it can keep going on and doing this amazing science for many, many years to come. Can we go to the next slide, please? So what I have been doing is, compared to Spitzer, Webb has absolutely revolutionized our capabilities. And this just gives you an example to start off with of an imaging field. The one on the left was taken by my former boss. And the one on the right is taken by Webb in the very first commissioning stage. And I have to say, I've never been so happy for my work to be completely outdated in one fell swoop. But you can really see the change in what you can see in the stars and the structure of space. And this is actually not our own galaxy. This is a nearby galaxy. So with Webb, we've really got a revolutionary change in capabilities, both with imaging and spectroscopy, which I'm going to show you in a little bit. Can we go to the next slide, please? So I've been busy taking stunning pictures. Every single picture here that you see is one of mine, and I love it. So this is a combination of old dusty stars, young stars, and star formation regions and nearby galaxies. And in this image where the cursor is currently over, I've asked for over 160 hours of time of spectroscopy to look at many of these objects within there to try and get a similar database to what you have with Spitzer and what you're looking through now. But that is judged by a panel, and I'll find out in sometime in the new year if that gets time. But as there's an oversubscription rate of these requests of about 8 of them will fail, only 1 of them will get through. So every 9 proposals, only 1 gets through. We want to try and find the best targets. And this is where you all come in, because you're helping me find the best targets for spectroscopy by going through Spitzer's database. So can we go to the next slide? So Webb is not just a very pretty camera for taking images. Most of the data actually is in terms of spectroscopy, both at slightly shorter wavelengths in the near infrared and then in the mid infrared with the MIRI. And this instrument was what was built in the UK and led in Edinburgh. And this operates at the same wavelengths that your Spitzer spectra do. So this is very comparable in terms of wavelength coverage and the type of science you see. But I'm going to show you some spectra now. So if we go to the next page, what you can see here is some of the very first data taken from the telescope. And so there's an image, and the way the spectral instruments on Webb work is you can take an image at the same time as you can take a spectra. And so you get both, you get the 2D spatial information as well as the light breakdown. And this is really powerful because then you can see differences across a small part of the sky. So this here, there's a field in a white box shown. That's zooming in on one of this. That's a galaxy nearby. Now, in the center has an active black hole. And in the bottom plot, that shows the spectra from the center of all the material and dust falling into the black hole. And then the top plot of the spectra shows the gas outside that supermassive black hole and what that looks like. And as you can see, the two spectra are very different. But with Spitzer, what you would see is a combination of those two things just in one spectra. But with Webb, you can actually separate that out as well. So it's a very powerful tool. And this is why you want to find these amazing follow-up targets to see and do this type of science. Can we go to the next slide, please? So here you go. This is maybe a bit more familiar to anyone who's looked at the data so far. This is in grey, shows the Spitzer spectra, the low resolution data. In blue, you're seeing the high resolution Spitzer data for the same object. And in red, you're seeing the JWST data of the spectra of the same object. And what's very cool about this is one of your 50 training samples as well. This spectra is in that training set, at least obviously not the JWST one, but the grey spectra is in one of those 50 objects. And so we looked at this and we used this object to calibrate the telescope and work out actually how powerful this was. And what you can really see is the power of where Webb comes in. What you're doing is you're mostly looking at these broader features, the dust, and you can see between Webb and Spitzer, they follow the same general pattern, the same squiggles up and down, the same emission features. But what you can really see if you look around 16 microns, there's a very sharp peak. Yes, perfect. The resolution and sensitivity of Webb, you are really seeing these narrow emission lines. So what's very broad and not very well defined with Spitzer is very clear with JWST, and you can see much more of those lines and a lot more finer detail as you zoom in and zoom in and zoom in. And that gives us a lot more powerful ways to work out what the physics is happening around this object. So you'll see a lot more these narrow lines as you go in, and they're all real, they're not noise. And so this is one of the reasons why I want you to look at the Spitzer data, because in general, the broad shape is the same, but we want to then go back with Webb to look at in a lot more detail the really interesting objects. Can we go to the next slide, please? Again, this is the same spectra. I've zoomed in here and highlighted a dust feature in purple, and then some things called PAHs. These are your burnt toast, these small carbonaceous molecules. And with Spitzer, you can see, this is the JWST spectra, but with Spitzer, you can see these bigger ones, like this big purple one you can easily see with Spitzer. But if you go all the way to the shortest wavelengths, less than 5 microns, there's some very, very tiny features here, which you cannot see in the Spitzer data, but with Webb, you can really see. And you can really zoom in. This is just a general overview plot. And this is one of the reasons why we want to do this project as well. So you're helping me find targets to follow up. Can we go to the next slide, please? Again, another one. I think this one is also in your training sample. This is a nearby supernova. So this is a star, a massive star that exploded in 1987. And I've just shown here the 4 components of the Spitzer spectra overlaid. And then if you can go to the next transition, you can see the broad shape is the same, but with Webb, you can really see all these lines and all these details. The shape, again, the broad shape is the same, but it's a lot less noisy, it's a lot uncertain. You can see a lot more clear details. And actually with this data, what you can see in the left is actually this supernova itself and what's left behind. With the 3D information, you can highlight different areas. And in the center here, there's a very purple thing right in the center, and that's an argon line in the spectra. So if we go to the next slide, what we discovered, actually, that is a neutron star. So that's the very first time we've seen an actual neutron star. This is one of the densest things known in the universe, which is not a black hole. They're about 10 kilometers across, and each bit of material of a neutron star, a teaspoon of that weighs the same as about as Mount Everest. So these are very, very dense, compact objects. And by following up the Spitzer data with Webb and this new fantastic technique of being able to isolate different components of where it is, we can actually see the birth of a neutron star in this well-studied object which exploded around 38 years ago, which I think is just fantastic. And so this is some of the science that I've been involved in. Can we go to the next slide, please? Again, this is another example of early science. You can again isolate some of these lines. So the left-hand figure at the top shows the 2D structure, and then it shows areas of where we observed with the spectrograph. And then here on the two other images, the pictures are just us isolating a line. So here it's either helium or neon from the spectra. And you can actually look at the 3D, the structure of the lines in space that look very different from the full object. But we can also analyze that from the spectra. So we need the spectra and that imaging capability to work out and make 3D images and maps of these objects now. And that's a revolution that JWST can do. Next slide, please. Again, just there's lots of cool science and spectra coming out, which I don't think has been highlighted from Webb. Many very pretty pictures. This is a star formation region. So I'm asking you to try and identify young stellar objects as part of your science cases. I'm looking for the evolved stars, the stars that are dying and the stars that are in the process of formation. And this is one that's in the process of formation. And what's cool about this is there's lots of things called ices, which are not water ice, though in some cases it can be, but you can have ices like methane in ice form because these objects are very cool and dense. And you can see all these interesting complex signatures in their signature, spectral signature, which may even potentially point to signs of life eventually, which I think is just very cool. These are the building blocks of new stars and new planets, which we couldn't see before. We need these higher resolution details. So we want to try and find these objects and look at them with these new spectrographs. Next slide, please. And this is all the gory details. You are seeing so many new things. We're seeing so many different features, which are not in our very simple yes/no spreadsheet. There's this, one of the things I asked you to look for is an ice feature, a carbon dioxide ice feature at 15 microns. You can really see that in green highlighted in all the structure here. That's a very key signature of a young object really embedded. You can see silicates and emission, and you can see all these lines. And what I think, oh, it's not on this one. Can you go to the next slide, please? Some of these are, we don't know what some of these signatures are. In this plot, we see all these ices and all these other complex molecules, but some of them we haven't identified what they are yet. And I think that's a new exciting time. So it's okay to be uncertain. If you don't know what something is, make a note of it, say it's there, but it's very, it's not bad if we don't know what it is. You want to say it's there, obviously, but if you don't know, and it's good to be comprehensive. There's no point making up something if you don't know what it is. And this is actually a published paper. And so this person has told the world, we found this thing, but we don't know what it is yet, which I think is a very good way of doing science. And what is key in here, and what I'm going to move on to now, is the next few plots are all data from Webb, but they all show a continuum fitted to the data to actually be able to do the science. So this dashed line you can see at the top is where people have drawn a continuum. And so drawing a continuum, which is part of the tasks of identifying different species, is a very key component of a scientist methodology in spectra. And to do this, you need to know that all these objects are in absorption. So you fit normally a continuum, you use the shortest part of the spectra, so the parts of the blue, and then you continue trying to draw a smooth curve to identify the features. Yes, thank you. I appreciate here. And again, there's several components which I ask for, looking for. So silicates and absorption, this ice feature, these are all very common in the spectra. The C2O blend is a very common signature. So if we go to the next slide, I just want to give you an example. This is an exoplanet. So this is a planet orbiting another star. And again, they've drawn a continuum. There's a feature here. This is looking at the atmosphere of this planet. And what was discovered by drawing a continuum, you can actually say there's a quartz feature here. So quartz, the mineral, I think you've all seen, you were quite common with that. That signature here, that bump, here is from quartz in the atmosphere of this planet. And without drawing that continuum line underneath it, you wouldn't, it's very key to identify this, because then you wouldn't know, if you can't identify the continuum, you wouldn't know actually this atmosphere then is actually made of vaporized quartz that's blocking the light. And I just think that's a very cool science result. Can we go to the next slide? And then finally, another example. This is another galaxy nearby. I say nearby, it's a very long way away, but in astronomy terms, it's nearby. It's face on. And again, we've drawn a continuum here. All those red points in the figure are where the team has used to select its continuum point and then use that to draw a smooth line. And then from that, you can see there's two features underneath it, which are silicate. So that's your 10 micron feature and your 18 micron feature in absorption. And that tells us there's lots of material there that's all falling into this black hole. And actually, we can recover from this object a lot more interesting features, and then we can actually make a 3D map of this black hole galaxy with lots of star formation going and material falling into the black hole. And so it's very powerful. But key to this is getting the features identification correctly and drawing your continuum. So, and this whistle-tops tour of JWST science, that's the science side of things. And I'm going to start now on a tutorial on actually how do you draw a continuum. So can we go to the next slide, please? So I think I've pressed upon that identifying a continuum is key for any science and identifying features. And normally these things follow a very smooth line. You don't want to have, it doesn't have to be a straight line, it can be a curve. But what you want to do is always draw a smooth continuum. You don't want to be making squiggles as you go. And typically it will look like this curve that's falling in most objects that you're looking at. And the reason why that is that's what a black body looks like, which is typical of any star. Most stars are black bodies that don't have any dust, and so they have this continuum that just falls like this smooth curve that you're seeing in this image. So if in doubt, try drawing that shape first in any form of object that you see. And if you can try and draw a curve like that, that's great, and you can have an idea. So because this object follows a smooth curve and there's nothing above it, that means you can say no, there's no infrared excess. The way you answer that question is if there's anything above or below this curve in terms of features or a large amount of material, then that's how you answer that question. If it follows a curve like this, then there's no infrared excess. It's just a normal stellar object with not much going on. And there's probably not going to be a target to follow up with JWST. Can we go to the next slide, please? So here, this is another example of an object, which I'm going to show you how do you draw a continuum with this? Well, the best way to do this is to look at the green part of the spectrum at the very start. Yeah, this part here. If we go to the next slide, or the next, yeah, you've got that highlighted, you've got the green bit, and you know that typical continuum shape. So what you do here is you look for that green part of the spectrum in almost all objects, and you see if it's rising or falling, and you see, can you follow that with a curve? And if you can, great. I think the next slide shows that in action. Yeah, so there we go. We've drawn that sort of shape, that smooth falling curve. And one of the things to really look for is look for peaks. So above that curve in the green, there's a thing that looks like a bit like a triangle. Wherever that peak is, it can either be down or it can be up. You want to be drawing your continuum underneath anything that's a peak. You want your peak to be on the opposite side of the continuum. So I think you can, there's more objects in, if we go to the next slide, maybe we've got more examples of this. Again, here, there's a little peak in the green. It looks a bit like a triangle. So you want your continuum to fall at the widest part of that. So you want to draw your continuum underneath. So if we show the slide with the continuum on, it falls, okay, quite a thick line, but it falls underneath that slight peak in the green at the widest point. I hope that's clear. Yes, so that's where you'll draw your continuum on that object, and then you would just, the key is making it smooth. So you just continue drawing. You start off your drawing and then you estimate where it'll be. And because here there's lots of material above that line, you would say then this object has an infrared excess. If there was nothing there, it wouldn't be an infrared excess because this the next three segments have lots of material. You would say it has an infrared excess. Can we go to the next slide, please? Okay, so here we go. This is a hard one. This is a really, really red object. It's lots of dust. What is going on? Well, again, you want to look at the green bit right at the start. Can you draw a line? You want to try and draw something smooth. You want to see if there's any peaks or troughs. Where are most of the peaks or troughs? If you then look further along as it tends to be more or less a straight line. So what you want to do is draw your continuum. Again, the broader bits are any features or squiggles. You want to be, you don't want your continuum to be falling and tracing that. You want to draw your line and basically skipping over that data on the other side. So if we draw a continuum here, you can see that the two features at 10 and 20 or 18, I've drawn my continuum, so those are on the opposite side of the continuum. And you can see that they're really in absorption. And you just quietly follow, and it's normally a black body. This one's a very cool, dusty object, so you can have a turnover later on. And you can see if the majority of an object is following a smooth line, you follow that and see if it starts to turn over. You keep drawing it so it starts to turn over. And then you can see around 35, there's a bit of material that falls above the continuum here. Because if you continued going straight, which is valid, you would end up with not a smooth line, and those peaks would be on the wrong side of the continuum. So that's how you decide. It doesn't matter too much if towards these longer wavelengths, if it falls out, if you don't get it quite right there. It's better at the shorter wavelengths where you really are more certain of the data. But this just gives you an idea, is there some material still going on at these longer wavelengths? I think that's it for my slides, unless there's any other objects. Aha, here we go. This is another one with a very interesting feature. Look at the green part of the spectrum and then small emission and absorptions. So in this top plot, this is all the same object. It has a high resolution spectra and a low resolution spectra. If you start at the green and you start to just draw your lines, you look for where those sharp peaks are. And yeah, you want to continue. Yes, perfect, Mike. This is excellent continuum drawing. So you want those the sharpest peaks to be on the opposite end from where your continuum is. If we draw the continuum, there we go. We've identified the peaks. And then if we draw a continuum, and you just keep following. It's really good if you can print this out or just have and you just use your hand to nicely draw. And it's just a smooth process. You don't want to be changing. You just see where it naturally flows, and then that shows you at 10 microns you've got a feature that's in absorption. And actually then this other plot on the other side, you would then use this 10 and you would see this actually is the bottom, but the start of this data actually corresponds to the dip here. And if you wanted to combine those two spectra together, you would continue drawing that continuum across the way. So my tips for drawing a continuum are: look for peaks, use the green data at the very shortest wavelengths to guide you, and it's normally a smooth curve for drawing a continuum. If you find you need to make it disjointed, you are probably going a bit wrong. So if there's any questions or answers, I think this would be the time to ask me any tips. Oh, the final one. Okay, how do you do it on this one? This final object. So like I was saying, this is an object with lots of dust. And the reason I know that is you look at the green part of the spectra, right at the very start, the shortest wavelength. You can see your triangular peak. You know you want to draw a smooth continuum underneath that. So you would start off from the shortest wavelength. You're drawing underneath, so you follow that green, and then you'd end up with a continuum. And then there's lots of material above the continuum. So then you can tick, yes, there's lots of infrared excess here as well. And then from that, you can look at what features are present. So that's how you do it. You find your little peak, you find your green, and you draw your nice smooth line. And I hope that is identifying continuum, the basics for finding these objects. And then, like I said, this is all very key, because then actually in any scientific method, you need to have that right before you can start to identify the other material, what's around these young stars, these galaxies, these dying stars and planetary atmospheres. So thank you very much, and I'm happy to answer any questions you may have.
Thank you, Livy. Just looking, are there any questions in the chat? Camera's just gone off. Nothing in the. I don't see anything in the chat, and if anyone's there, we go. There. Well, if there's no questions for Dr. Jones, we'll finish off here, and we've just recorded this, and then we'll snip it down, and then we'll make that available for you so you can watch it and go through it again. But as Livy stressed, the continuum is key. And I know I don't want to use the line of best fit word, but your teachers will probably have shown you how to draw a nice smooth line to actually go through data. So it's worth bearing that in mind, because if you're starting to have points of inflection and such like, then you've not drawn a proper continuum. It could be fair to say, wouldn't it? If you're going up and down at any point, that's not a line of best continuum. So next steps for everyone. We have a question here. What's the significance of the little peak which is green? And I've just lost the question, Neil. Where's that gone?
Oh, I've seen it. What is this little peak which is in green? So any peaks are either from atomic lines, so any really, really narrow peaks. So these are the very sharp features, are from atoms that have been either ionized or are in the surrounding gas around that object. And any of the broader ones are a dust feature. So the one at that wavelength is actually a PAH, which is a polycitric aromatic hydrocarbon, which is again like your long chain carbonaceous molecules. So what we want to do and actually do in most science is then actually go through all those peaks we see, and we want to identify what they are and what energy state they're in, how many ionization levels they're at, if it's an atomic emission line. And then from that, we can work out the density of the environment. You can work out the temperature. You can work out how much radiation they're experiencing. There's lots of actual physical properties we can work out once we know what those lines are. And actually, for more distant objects, you want to identify patterns of those lines. And then actually you can use that to work out the redshift of the object. So that's how far away your object is. They won't be at their rest wavelength. You need to see the patterns of many of these lines, realize they're all slightly off, and then correct for that. And that's how we work out the distance to these more, these very far away galaxies. So they're all very cool things to find, but you can't find them first until you know. You need to know vaguely where they are. You need to compare it to atomic databases or other databases, and you need to make sure you can identify them correctly. And some of them, like I said, I showed one where we found a feature, but we don't know what it is yet. And that's the exciting time, is identifying new things in space, which I think is, we're very much on a new path of discovery at the moment about many objects with this new telescope.
And actually, I have got a question that came in by email. With AI and automation of this process, people are talking about machine learning and such like. What's the validity of that?
The problem is that you're looking at objects at very different distances. So if you get all these lines that may occur, other lines can also appear at the same wavelengths, and it needs a lot of interpretation. And AI is not very good at drawing continuum. It's not very good at identifying things, and there are many different calibration effects as well in the spectra. So it could be a noise spike, which can be flagged. What is good AI is good for is once you identify your continuum, and then you what you do is you subtract that away. You can then use different programs to say how many spikes are there above that line or below that line. And then that's very good at processing so it's more signal processing than AI. But it's not very good at drawing continuum at all. And so it misses things, especially the broad features, and it's very bad at identifying them because every single one of these the atomic emission lines more or less stay the same shape, but they can move in wavelength space. But you can get different combinations. But the broader features can be affected a lot where they peak, the shape of them, if they're above or below the continuum. The size of the grains change those positions, the temperature of the grains, if they're spheres, if they're long needles, if they're fluffy balls of things, actually all change the position, and AI is not very good at identifying any of that at all. In fact, it's terrible at identifying that.
Excellent. Thank you. One more, I think, Neil. Nope, I can't see that one. In that case, what we'll do is we'll wrap it up there. Thank you for your continued support of the project, Dr. Jones. And it's, the project's been running now five years, and we're still looking at getting to the point where we're looking at stuff that has been seen before. So, students who are actually making a difference, it is actually valid research that you're doing, which is helping other people, and who knows what might be found in the future. So thank you everyone for attending. I'll be in touch with a link to the recording. And any questions, as always, please just ask. Bye then, everyone.